All right, let's get right into it. We're going to tackle one of the biggest, most fundamental questions in all of artificial intelligence. How can a machine, or anything really, learn to predict the future just by looking at a handful of past examples?
I mean, it sounds kind of like magic, right? Peeking into the future. But what if I told you the core principle behind it is something you already do, probably without even thinking about it? It all boils down to a surprisingly simple, almost ridiculously simple idea. Just counting.
So, here's our game plan for today. We're going to start with the absolute foundation, which is just simple counting. From there, we'll level up and see how to handle more complex queries. Then we'll get to the really cool part, this conditional given twist. After that, we'll add another layer by weighting our samples. And finally, we'll tie the whole thing together and see why this is so crucial for AI. Sound good? Let's dive in.
Okay, first up, the foundation. Before we even think about any complicated formulas or anything like that, let's just strip this whole idea down to its bare bones. Seriously, everything we're about to do, it all starts with just counting. Simple as that.
All right, so say hello to our data set. This little table right here, with just 10 samples, is going to be our best friend for the rest of this explainer. Think of each row as just one observation, one event that happened. And for each event, we know the state of 4 things: A, B, C, and D. Trust me, we're going to get to know this data inside and out.
Now, I promise this is pretty much the only formula you need to keep in your head. It's just favorable cases divided by total cases. I mean, think about a coin toss, right? What's the probability of getting heads? Well, you count how many ways you can get heads. That's 1, and divide it by the total number of things that could happen, which is 2, heads or tails. So, 1/2. That's it. That's the entire logic we're going to use.
Okay, so let's put this to the test. Let's ask our data a really simple first question. Looking at our samples, what's the probability that variable C is in the state we're calling -C?
So, how do we figure this out? Easy. We literally just scan down that C column and count every single time we see a C. Okay, there's one, there's another. Let's see. Yeah, if you go through the whole list, you'll find there are exactly 6 of them. So we have 6 favorable cases.
And just like that, we have our answer. We take our 6 favorable cases, divided by our 10 total samples, and we get 6 out of 10, or 0.6. See? It's really that simple.
All right, cool. That was the warm-up. But what happens when our questions get a little more interesting? When they involve more than just one variable at a time.
So what if we have multiple conditions that have to be true? This time, we're asking for the probability of a sample where A is negative and, at the very same time, B is positive.
Now, the cool thing is, the logic doesn't change one bit. We're still just counting. The only difference is, a row only gets to be counted if it satisfies both conditions. So let's look together. First row, nope. Second, nope. Ah, wait, here's one. This row has -A and +B. Perfect. Okay, let's keep scanning, keep going, and yep, there's one more down at the bottom. So that's a total of 2 rows that fit the bill.
So, with 2 favorable cases out of our 10 total samples, the math is easy. 2 divided by 10 is 0.2. So even when the question gets a bit trickier, the fundamental idea is exactly the same. Favorable divided by total. That's our mantra.
Okay, now we get to the really, really cool part. This is where things go from just counting stuff to actually making intelligent inferences based on new information. Welcome to the conditional given twist.
So you'll see this notation, P of A, a vertical line, then B. And all that means is the probability of A given that B is true. It's a huge shift in thinking. It means we're not looking at all 10 samples anymore. We're imagining a world where we already know for a fact that B is true. So we call B our evidence, and A is the query. It's what we're asking about inside that new, smaller world.
Let's make this super concrete with an example. What's the probability of -B given that we already know for a fact that D is -D? And this is just a simple 2-step dance. Step 1, we find our evidence. That means we throw out every single sample that doesn't match our given condition. What's left is our new, smaller universe. Then, step 2. Inside that new little world, we just count our query cases, exactly like we've been doing all along.
And here is step 1 in action. We look for all the rows where D is -D. We find 5 of them. And what about the other 5 samples? Well, for this question, they might as well not even exist. We ignore them completely. Our new total cases, our new denominator, is now 5.
All right, on to step 2. We're only looking at those 5 highlighted rows now. So within that little group, how many of them also have B as negative B? Let's count them up. There's 1, 2, 3, and, yep, 4. 4 of them satisfy our query.
And this is the key insight. Notice what happened. Our denominator changed. We are no longer dividing by 10. We're dividing by 5, the number of evidence cases. So our probability is 4 favorable cases divided by our 5 evidence cases, which gives us 0.8. We've just officially updated our belief based on new evidence. That's huge.
Okay, we're almost at the finish line. But let's add one final layer of realism. Because in the real world, not all examples are created equal, right? Some are more important than others. So let's talk about weighted samples.
The shift in logic here is so simple, but it's super powerful. Before, we were just counting samples. 1, 2, 3. Now, with weighted sampling, we just sum the weights of the matching samples. So instead of counting, we're adding.
So let's do our last problem over again, P of minus B given minus D, but this time with weights. The steps are the same. First, find the evidence where D is minus D. But instead of counting them, we add up their weights. So that's 0.3 plus 0.2 plus 0.3 plus 0.2 plus 0.3, which gives us a total weight of 1.3. That's our new denominator. Now within that group, we find the ones that also have B as minus B. We find those 4 rows and we add up their weights. That's 0.3 plus 0.3 plus 0.2 plus 0.3, which comes out to 1.1. So our answer, it's simply 1.1 divided by 1.3.
So there you have it. We've gone all the way from just counting on our fingers to figuring out weighted conditional probabilities. Now, for the most important part of all, why does any of this matter? Let's connect it all back to AI.
Let's just recap the whole journey real quick. We started with simple probability, just favorable over total. Then we did joint probability, just count the samples where everything is true. Then came the big one, conditional probability. Shrink your world down to the evidence first, then count. And finally, weighted sampling. Just sum the weights instead of counting. These 4 simple ideas, that's basically the engine that drives probabilistic inference.
Because, what we just went through, it's not just some abstract math exercise. This is it. This is the foundation of how modern AI systems actually learn from data. When an AI forecasts the weather, or helps a doctor diagnose a disease, or even just recommends what movie you should watch next, it's using these exact principles. It all comes back to learning from examples. Which leaves just one final question for you. If you had the right samples, what could you predict?